All right, hello everyone. So it's that time again for the next Physics 232 video. In the last video, what we tried to imagine doing was to try to fit data to a nonlinear function. So this is a function that we could not write the parameters in the form of, say, a1 times some function of x plus a2 times some other function of x, and so on, where those functions, f1 of x and f2 of x, don't involve the parameters at all. So we imagine now that we have a more complicated function to fit to, and the strategy that we approached was the simplest one we could imagine. It was to select a range of possible values for each of the parameters in the fit, and then just to set up a grid of points. So imagine you could have an axis where, imagine we're doing a 2-parameter fit, and so maybe this is the parameter a1 and this is the parameter a2, and over here is what we decided would be the minimum value of a1, and over here was its max value, and then we have the same thing for a2, some minimum and a maximum. And the other thing we did is we said, well, we're also going to pick a step size, and we'll set up this grid where the spacing of the grid lines is our step size. So this would be here, would be our step size, say delta A1. And then we have a step size for A2 as well. And so maybe this is delta A2. And we just go and we calculate chi-squared at every single point on this grid, and we just make a table of the values of chi-squared and the corresponding parameters a1 and a2. Now I'm drawing this as if there's only 2 fit parameters, but you know, I can't draw it for more, but you could imagine just generalizing this to any number of fit parameters. Okay, so then we select the combination of a1, a2 that produces the minimum possible, or the minimum value of chi-squared. Okay, and so let's say that those values that produce the minimum in chi-squared are like a1 star and a2 star, and maybe a1 star sits over here and maybe a2 star sits over here. And so this is the point that will produce our best fit parameters. What we haven't talked about is how we're going to get the uncertainties in a1 star and a2 star. And so what are the uncertainties in a1 star and a2 star? So for example, we might call it sigma 1 and sigma 2. Okay, so let's do the usual thing that we do. We imagine that we perform an experiment and we measure x versus y so we have x and yi plus or minus sigma I for I equals 1 to n. Okay, so we fit the data to a model that depends on AK parameters, where k can be 1 to m. Okay, but now there's no restriction on the form of that model. It could be as complicated as you like. So y depends on x and these m parameters. So by whatever means, like maybe the grid, kind of the grid search that we just discussed at the top, however we do it, we find the set of parameters that minimizes chi-squared. So chi-squared, remember, was to take the measured y value, subtract it from the calculated value when x is xi. We're going to weight this sum by the uncertainty sigma. We'll square that all and add it up for all the points. Okay, so let's just recall the origins of chi-squared. So recall that chi-squared came from the fact that the probability of obtaining a set of data x, y plus or minus sigma from parameters a1, a2 up to am was given by this likelihood function that we had developed. So this is a function that depends on the values of the parameters, and it was the probability of measuring a result y1 when x is x1 times the probability of measuring y2 when x is x2, and so on for all the points. And so here, this P1 is the probability of measuring, say, y1, let's be more specific, measuring a result between y1 and y1 plus delta y when x is equal to x1. And then the same thing for 2 and 3 and all the way up to n. This thing was called our likelihood function. And we were employing this method of maximum likelihood, so we're going to maximize this probability. That is, we adjust the values of a1, a2, a3, and so on until that probability is its maximum possible value. Okay, so using our product notation, this likelihood function could be expressed in this way. And we had previously written down like what P1 and what P2 and what P3 all looked like. And they were these Gaussian functions. So what we really have is a product of Gaussians. Okay, so, and the Gaussian has this exponential in it. There's a minus 1/2. And then we had yi minus y of xi over sigma I squared, like so. All right, so we've got this product of exponentials, and we know that we can take a product of exponentials and we can write that as an exponential of a sum. So we have this prefactor that we're not going to do anything with that. That just stays the same. But then the exponential becomes a minus 1/2, and then it's the sum of I equals 1 to n of, let's see, yi minus y of xi over sigma I squared, like so. And this sum is exactly what we called chi-squared, and so that's that's just a little refresh. Oh, I don't like that. That's just a refresher of where chi-squared came from. So our likelihood function then is this prefactor times the exponential of minus 1/2 of chi-squared. All right, and I think I'm going to call this something number sign here. So let's suppose that we've done this minimization. We've tuned all our parameters so chi-squared is as small as possible. Minimization of chi-squared. Get out of here. Oh, come back, pen. All right, so yi minus y of xi over sigma I squared. So what I want to think about doing is doing a Taylor series expansion of chi-squared about its minimum point. So let's remember that y is a function of all of these parameters. And so this is the y that is sitting in here. Okay, so it's the y that we're using to do the model calculation of y at xi. So we're going to Taylor series expansion of chi-squared about its minimum with respect to one of the parameters aj. So what that means is we imagine that we found all these parameters that do the minimization, and so maybe it's an A1 star and an A2 star and an A3 star all the way up to AM star. Those are all the starred values are the values that produce the smallest chi-squared. And so we're going to leave all of them at these values that we found, and then we're going to select one parameter, the jth parameter, and we're going to allow that one to vary a little bit away from its minimum. So a Taylor series expansion looks like, so the first thing you do is you just evaluate the function at whatever your expansion point is, and in our case our expansion point is the minimum. And so this is just some number, chi0 squared. And then Taylor series says, well, then you take your variable and you take the difference with your expansion point. Often you would expand a function about 0, but we're not doing that this time, so we don't have just an a, we have an a minus our expansion point, aj star. And then it says take the derivative of the function, which in our case our function is chi-squared, with respect to your variable, which is aj, and then after you've done the derivative, evaluate it at aj star. So that's the 0th order and the 1st order term, and I'm going to keep one more. So we would get 1/2 aj minus aj star squared, and then we take two derivatives of chi-squared with respect to our variable. I need to put my square there. And then after you've done those two derivatives, evaluate at aj star, and then if we wanted to, we could include more terms. Okay, so let's just imagine that chi-squared as a function of aj has some shape. We're expanding about a minimum, right? So we expect this thing to have a minimum somewhere, and that minimum is over here at aj star, and chi-squared evaluated at the minimum point results in chi0 squared. So this is chi0 squared. Okay, and then what we do is we say, well, let's think about the second term, this first derivative of a chi-squared with respect to aj, evaluated at aj star. I mean, obviously the first derivative is just finding the slope of a tangent line, but a tangent line at aj star is horizontal. It has a slope of 0. And so that means, because we have 0 slope, d chi-squared daj at aj is equal to aj star is equal to 0. Slope is 0. Okay, that's nice, because what we can do is we can just throw away this first order term in our expansion. Okay. So what that means is what we have left is chi-squared is chi0 squared plus, let's see, I'm going to write it as 1/2 times 2 derivatives of chi-squared evaluated at the minimum point. Okay, and I'm going to put this all separated out. And this is aj minus aj star squared. And so let's take all of this stuff in brackets and just label it as b, right? Just some number b. And if we do that, then what we end up with is chi-squared is equal to chi0 squared plus b times aj minus aj star squared. And this is a quadratic equation for chi-squared with respect to aj. And we know what a quadratic equation looks like. We could draw it in here. And what this is really saying is that very close to the minimum, the shape of our chi-squared should look like a parabola. The minimum point of the parabola is at chi0 squared, and then b is this parameter that tells us how steep the parabola is. How quickly does chi-squared increase as we move away from the minimum? So we have 3 unknowns here. So 3 unknowns. So if we could produce a set of 3 equations, then we might be able to solve that for these 3 unknowns, and then we would know something about the shape of chi-squared as we move away from this minimum point. And before we do all of that, let's just think about why we might care about this. So let's imagine 2 cases. This is chi-squared as a function of, say, aj. And we'll have one case like a red case. And so let's imagine that in this red case, chi-squared varies like this. And so, okay, well, let's stick with red. And maybe the minimum is over here, and this is aj star. Okay, and then we have a blue case where when we look at how chi-squared changes, it changes like this. So they're both quadratic. It's just that one changes rapidly when we move away from the minimum and one changes slowly. So this blue case would be large b. And this red case would be a small b. Okay, so if we think about this a little bit, what is it really telling us? It tells us that in the red case, if we sit at the minimum and then vary the value of our best fit parameter, there's not much change in chi-squared. And so chi-squared's pretty insensitive to relatively large changes in AJ star. And so the red case, chi-squared is insensitive to large variations in AJ star. So that means if our minimization doesn't change much when we vary the parameter, that parameter has a large uncertainty. So we say small b corresponds to large uncertainty. Large uncertainty, say sigma j. Okay, obviously the blue case is the opposite. Blue case, chi-squared changes rapidly as AJ deviates from AJ star. And so in this case, we have large b corresponds to small sigma I. So what we expect then is that we might guess that the uncertainty in our parameter is in some way inversely proportional to b. This is not going to turn out to be exactly true, what I've written down here, but it's maybe a first guess. Okay, so what we're interested in then really are trying to determine these three unknowns. Chi0 squared, we'll find maybe in a few videos later that there is some reason to be interested in the value, but for the moment, it's really b that we're most interested in. And then, in fact, what we could do is, if we did like a grid for finding AJ star, like we did at the beginning of the video, we may find that our grid was coarse. And so we didn't actually find exactly the minimum point. We found something close to the minimum. And so this little procedure we do actually might help us refine the best fit value, AJ star. So if we know the value of chi-squared at 3 points AJ near the minimum, so near the minimum means that this is at a point where chi-squared is approximately quadratic. Then we can set up a system of three equations to determine the three unknowns, chi0 squared, b, and aj star. Okay, so let's draw a big picture. Aj, chi squared, and so we're imagining this is quadratic in this region. And so we're going to pick 3 points, and maybe the 3 points are something like this, okay? And what we'll do is we'll call this point A1, and this is chi1 squared. And I'm going to actually move my points a little bit. I want to make them equally spaced, and I don't think I quite did that. So let's put this one over here and this one over here. And so I'm going to call this A2, and this is going to be chi2 squared, and I'm going to call this A3, and this will be chi3 squared. Okay, and so let's imagine we've done this so that the spacing between A1 and A2 is delta A, and the spacing between A2 and A3 is also delta A. Okay, so let's see. We know that chi squared is quadratic in this region. That was our requirement. So we write that chi1 squared is chi0 squared plus b a1 minus a star. And so a star corresponds to the true minimum here, which is something we may not know. I'm going to omit the j subscript, but you have to remember that we could do this for any one of our fit parameters. We're selecting one of them at the moment. Okay, then chi2 squared is chi0 squared plus b a2 minus a star squared, and chi3 squared is chi0 squared plus b a3 minus a star squared. Okay, good. So the way we drew things, A2 plus delta A is equal to A3, or equivalently, we could sub in A2 is whatever A3 was minus the step size delta A. And so I'm going to sub that into right there. And if we do that, we'll get what? Chi2 squared is equal to chi0 squared plus b. A3 minus delta A is A2 minus a star squared. So just reorganizing some of the terms in the bracket, we would have an A3 minus a star, and then a minus delta A, and then square the whole thing. Okay, we could also sub that A1 is A3 minus 2 times delta A, right? So if we go from A3, and then we subtract delta A and subtract delta A again, we get to A1. And we're going to take this expression, and we're going to sub it into right there. Okay, so then we would get chi1 squared is equal to chi0 squared plus b. A1 is A3 minus 2 delta A, then we minus A star, and then we square it. Or chi1 squared is equal to chi0 squared plus b. A3 minus A star minus 2 delta A all squared. All right. So I'm going to call this equation 1, I'm going to call this equation 2, and this equation 3. And what's known in these equations are the values of delta A, the values of A3, and chi1 squared, chi2 squared, and chi3 squared. Those are all known values. What's unknown is chi0 squared, b, and A star. But all of those unknown parameters are inside these three independent equations, and so we can solve the system of equations 1, 2, and 3 for the unknown parameters. Chi0 squared, b, and A star. So I'm not going to go through that process, but it's something you can do for yourself. And what you do is you find that A star is equal to A3 minus delta A, and it's chi3 squared minus chi2 squared over chi1 squared minus 2 chi2 squared plus chi3 squared, and then it turns out that there's a plus 1/2. Okay, the other thing, in fact the thing we'll be most interested in for the moment, is the b parameter, and it turns out to be the following. All right. So what we can do then is, oh, sorry, I just need to find the right set of notes here. Right. We can take our quadratic expression for chi squared and we could sub it back into our likelihood function. So let's return to the likelihood function, and I'll rewrite this again, but it's something we reminded ourselves of at the beginning. It had this prefactor, which will turn out to not be that interested in. And then we had written that it was the exponential of minus 1/2 of chi squared. So we're going to return to this function and we're going to sub in the expansion of chi squared, which was chi0 squared plus b aj minus aj star squared. So that's that quadratic. Okay, so let's just literally do that. We'll just write out our likelihood function again. So then we get exponential of minus 1/2 of chi0 squared plus b aj minus aj star squared, like so. Like I said, we're not going to be that interested in this prefactor, and so we'll just call it some constant a. All right, so what we have then is a, and we have an exponential of a sum of two terms, minus chi squared over 2 and minus b over 2 aj minus aj star squared. So I'm going to write that as a product of exponentials. So we could write that as the exponential of minus 1/2 chi 0 squared times the exponential of minus b over 2 aj minus aj star squared. Okay, chi 0 squared is just a number, so we'll take a times the exponential of minus that number, and we'll just say that's just some other constant a prime. And so our likelihood function then can be written as a prime times the exponential of, I'm going to do this in a little bit of a funny way. We have minus aj minus aj star squared over 2 times b inverse. Okay, so I took that b and I wrote it as 1 over the inverse of b. I want to compare this result to the Gaussian, I don't know, probability distribution, okay? So the Gaussian function was 1 over sigma root 2 pi, and then it was e to the minus x minus mu squared over 2 sigma squared. So we kind of have something like that. We have some variable, so the aj is like our x, aj star is like our mu, and so that means that over here our b inverse is like our sigma squared. And so if we make that identification, we can determine that the likelihood function becomes a Gaussian function for each of the aj parameters. Okay, in particular, the important result is that the sigma j squared is equal to the b inverse or sigma j taking the square root is 1 over the square root of b. And so that's something close to what we guessed. We might have guessed that sigma j was inversely proportional to b. I mean, really what we probably determined is that it should be the case that as b gets larger, the uncertainty gets smaller, and that's certainly what we found. So this sigma j is the uncertainty in parameter aj. So we had written down an expression for b. Where is it? The expression for b was right here. So if we take the inverse of that and then take the square root, that tells us what the uncertainty in parameter aj is. So let me write sigma j squared is the inverse of that expression that we had determined. So the process to estimate this uncertainty would be to calculate a bunch of chi-squared values near the minimum of AJ and produce a plot of those, and that plot should look quadratic. And if you pick 3 of the points in that quadratic region and you determine the step size delta A between those 3 points and chi1, chi2, chi3 squared, then you can calculate an estimate for the uncertainty in that parameter, AJ. And you do that for j equals 1 all the way to m, however many fit parameters you have. Okay, good. So that's where we'll stop. Maybe what we'll do next time is we'll make like an overall summary of our strategy for fitting nonlinear functions, determining the best fit parameters, and their uncertainties. All right, thanks very much.